Okay, let's go over the presentation for week 6. I won't address every point. I think that most of them are pretty easy to understand, um, especially the part about exercise is medicine. But yeah, exercise is medicine is not a new idea. The idea that exercise is medicine has been used for hundreds, if not thousands of years. The idea that exercise can be part of the treatment. It's a new trend to try and hook up, so to speak, physicians with exercise specialists. I don't think that you should pay for that to happen. I think you can walk in or set an appointment with a physician and get it to get it to be done by yourselves, to just sit with the physician and try and work with them. It's not really in their scope yet. It is something that for years has not been addressed. Getting physicians to understand what we can do as well. Some of them do, some of them don't. It's not because they're not intelligent. They're actually highly intelligent. They're just not taught to think that way. But I think that should be for free, and you don't need to pay for that to happen. Exercise should not contradict the treatment. It should be part of it. Sometimes it can be the start of the treatment, not always. Sometimes it should be complementary, completing the treatment and part of it, and it should be dynamic and not static. The plan should change according to the speed or lack of adaptations and improvement. In some cases, it can take years. Of course, when someone is on medication, we wonder about the relationship between the influence of medication on exercise and exercise on medication. In some cases, exercise can prevent the need for medication. In some cases, it can lower the dosage. In some cases, it can take someone off of medication. And in some cases, it can cause a change in medication from the more potent ones to the lessers. So that's the whole idea of exercise as medicine. I encourage you to go over the presentation. If you have questions, just shoot them my way if you don't understand anything. But it's pretty simple. We do say that when someone is on medication, a lifestyle change has to be made, and that could include exercise. What I mean by that is that you might be exercising perfectly and might not. But obviously it includes nutrition and stress management and your diet and exercising and so on and so forth. There's so many things that could change in your lifestyle that would accommodate the treatment that you're getting and influence it as well. And that includes, by the way, being knowledgeable about about the treatments that you're undergoing and what you can expect and what not, as part of stress management and as part of the plan. Okay, it's good to educate people what can they expect and what not, or when to expect something and when not to expect it. And then I brought here a few definitions of medicine, and you can find your own self with your abilities within those within some of the definitions. Um, Obviously, exercise, aerobic exercise can improve oxygen delivery, which is important to the function of the body. The lack of oxygen or sufficient oxygen that we call hypoxia, not even to talk about the radical situation of anoxia, the lack of oxygen, are not good, and we'll visit those ideas in pathophysiology next semester, as well as you will be visiting the mutual effects of exercise on medications and medications on exercise in your course exercise pharmacology. We can talk about what exercise can do and not do, and we need to know the limits. So exercise cannot repair deformities, but it can definitely be part of the healing process, help with that, and accelerate it. Okay, and part of the healing process is better oxygenation of the tissues and cells. We can talk about, improving range of motion, motor control, self confidence, which is very important, mobility, efficacy, body image, stability. All of those and more can be worked as part of a treatment to certain populations. We can talk about proprioceptiveness. Um, and of course, we want to avoid harm if I'm regarding to slide 13 while doing that. So we kind of answered the questions on slide 14 and 15. Yes, exercise takes time. So any adaptations due to exercise are going to take time, and that's why sometimes medications have to come first, but not always. Okay, definitely. Let's see. We talked about all this. All right, so the last point is that yes, exercise can battle, so to speak, to a certain extent, the influences of age and gender, but not completely, meaning that a person that exercises loses functionality at a lower rate than someone that does nothing. And then, yes, exercise might be the difference between someone having a fatal attack or event or not. But it also may be the reason for those fatal attacks. Sadly, we know that in cardiac rehab, that for every 1 million hours of exercise, we have a heart attack. Not necessarily a fatal heart attack, but that's the number. So statistically, we should expect it. We are trying to do everything possible to prevent that, but it's part of exercise. People might over react, might overdo what you told them to do. They just feel good, or they have an ego problem. They're trying to prove something. They do more than you prescribe. They work harder, thinking it will get them better results, and then it's too much for the system, and they collapse. Then we talk about old school medicine versus new school, and we're definitely part of that new way of thinking. It's not that new, but it's relatively new, and that's the comparison between do no harm and do less harm. Today we're thinking let's do less harm, not do no harm. Do no harm means that if a treatment that you're giving to someone might damage that person elsewhere, you don't even treat them. Today that's not the situation. So if you believe that even if a medication might hurt or injure the liver a bit, but without it the person will die faster from cardiac problems, then you give them medication for their cardiac conditions, and you understand that you might be hurting the liver. And you see that in every ad for every medication today out there. So we're not looking for perfect. We're looking for the least harmful treatment. Of course, you have to educate people. You have to inform them. They may refuse medication, but from the healthcare professionals aspect, I think that that's very important. Okay, so there's lots going on about that idea, but that's the bottom line of it. And let's go over body composition. The field of body composition pertains to the study and application of principles related to the relative contribution of different types of tissues to the overall composition of the body. When we talk about principles, we're talking about scientific principles. We're talking about it can be physical principles, it can be chemical principles, it can be physiological principles, and so on and so forth. There are multiple levels of definition, but by far the most common is comparing lean body mass to non-lean body mass. The idea of body composition comes from the idea that excessive fat, notice that not any fat, but excessive fat is unhealthy. So we want to use it to define overweight people or healthy weighted people, obesity, people that lack exercise, and we want to use body composition to try and understand that. We want to correlate that, and then we want to correlate it to diseases and conditions and mortality, which is part of what we have succeeded so far as humanity. Another very important assumption in the application of body composition assessment and estimations, just remember it's an estimation, is that mass is distributed evenly around the axis of the body, which is not completely true, but it's an assumption. So unless you have a 3D scan and you can compensate, sorry, let's move the camera a bit. If you can compensate for those deformities, you must assume that a person's mass is distributed in a 3D matter equally around an axis. It's also assumed that that it's not only around an axis, but mainly around the vertical axis of the body. So it pertains to the volume of the body and how mass is arranged within it. Of course, you can also divide the body's composition literally into its atomic composition, meaning you look at the molecules and the atoms and the ions, the substances literally that make it, the body up. So for instance, you can look at the percentage, you can count in theory or estimate or calculate the number of atoms in the body and then look at hydrogen as a percentage of that total. The mass aspect of that versus the atomic will look at tissues, different kinds of tissues and their weight, just to make sure that you understand. In physics, weight is mass times gravity. So in theory, if you live in a place without gravity, you don't have weight, you have only mass. So that is the end of slide 28. So hydrogen is by far the most common atom. Mass-wise, oxygen leads the list. So you can have less atoms that weigh more, and then their overall contribution to the overall mass or weight of the body is higher than the atom that has lesser weight, and that's the case with oxygen. What else? Of course, these two atoms play a crucial role in both these aspects because most of the body is water, and we know that water is H2O, so you have two hydrogens for every oxygen, and that is why you have a lot of hydrogen and a lot of oxygen in the body. Then you can look at the molecular division of the body. This division will pertain to what molecules, what molecules, let's say, produce the majority of mass, or what molecules are number one in abundance, and so on and so forth. So you can look at water because that's a molecule, lipids, proteins, carbs, DNA, RNA, etc. It's endless. It's millions of molecules that you can look at and in theory estimate or calculate their contribution. Um, and then the fourth one is the contribution at the level of a tissue and how that contributes to body composition. So it's not atoms, it's not mass, it's according to tissue. So adipose tissue versus muscle tissue, and so on and so forth. Um, then you can divide it according to the number of cells. That's a fifth option of dividing. In that case, non-human bacteria lead the list, especially in the GA tract. What else? So basically, what we see in slide 32, the more accurate your ability to measure something, the more accurate should be your ability to predict something. Okay, and that's why you can see that there's multiple points of measuring. For instance, in the skin fold measurement, right? We have 3 and 4 and 5 and 6 and 7, and the most accurate today is the 7. Body mass index. Body mass index, I think, is pretty simple to understand. It's exactly the math. It's the mathematical ratio or the mathematical representation of the idea that mass should be divided equally around the axis. In this case, the vertical axis. There are a few problems with BMI, 3 to be exact, if I'm counting correctly. The first one is that the formula for adults does not work accurately for children. So there's a difference between BMI for children and BMI for adults. With kids, it depends on their percentile according to age, and there's rapid growth periods with children, so that ratio is as unstable as it gets. The second problem is that because you're using mass and assuming that if the ratio goes up it's due to fat, you have a problem in the comparison between muscle mass and fat mass. For the same volume, muscle mass will weigh about 1.7 times more than the same volume of fat. And then you have a mathematical problem, a mathematical bias, that by taking height into the equation, there is already a certain relationship between height and the weight of the person to start with, because that's where the ratio is coming from, or the idea of body mass index is coming from. So to start with, you have one factor of the formula that automatically, under perfect conditions, affects the other one, and then you're dividing one by the other, you have a problem. Okay. Of course, don't forget that one of the mistakes is the assumption that mass is distributed evenly around the axis. The next thing is that you're looking at, this is not a mistake in the formula, but when you look at body mass index as an index or as a working tool, just remember that the number doesn't tell you where is the mass distributed. Okay, and we know by now that when you have fat around your belly, that is a risk factor, or elevated fat mass in your abdomen, that is a risk factor for cardiovascular diseases. But just from the number, you can't see that. And notice how careful this scale that starts at 18 and a half goes up to 25, which is normal, or within the healthy range or not associated necessarily with any risk factors. And notice how careful I am when I define that. We know that underneath that and above that, you're either underweight or above weight, and then obese, right? And we have obesity 1 and obesity 2 and so on and so forth. And it's might be it's a risk factor, and then it might be associated with diseases. In this case, when we talk about adults for BMI, the formula is validated for age 19. Let's see. What else can we talk? Oh, of course, when we're talking about age, in this case, the tables are talking about chronological age and not biological age. Biological age is your age according to the systems and their level of maturation, whereas 100% maturation of the system should fit an adult, and lesser than that, you're not an adult. Whereas chronological age, whoever's 18 is 18. I mean, if they were born on the same day of the same year at exactly the same time, they're the same age. Circumference. So circumference is based naturally and simply on the idea that every tissue has its contribution to body volume. Okay, so this is already a 3D issue, and hence circumference. One of the problems with this assumption is the matter of density, meaning the contribution is also density dependent, and then the ability of the tissue to be condensed when we measure, the assumption that mass in this case, or volume, is equally distributed throughout the tissue. That's a bit problematic. And of course, we don't want to be confused with the density weight relationship of tissues. So we want to, with circumference, weight is not an issue, but volume is. We believe that changes in bone density and bone, not density, sorry, weight, are neglectable in their effect on circumference. So we're basically left with muscle and adipose tissue, but not only. People that have been reported to have heavy bones showed 30 grams more weight due to their total body weight, due to their muscle, due to their bones. And that's obvious, obviously when you take 30 grams divided by an average person that weighs 70 kilograms or 154 pounds, that's not a major player or factor to affect anything. Taller people tend to have wider bones. That will affect circumference. And the question is, when you're taking circumference, are you taking in consideration a person's height? The location of where you're measuring has a huge effect on the outcome, because you're going to use it, you're going to put it into a formula, right? So you want to make sure that the points where you're measuring are the right points that have the most correlation to total body weight and density and so on and so forth. Skin folds, which you have already experienced a bit, has a high correlation with total body fat, or percent of total body weight. It's more, the more sites it has, exactly like in circumference, it produces a better result. But it disregards differentiations between brown and yellow fat, for example. Brown fat tends to be a bit more functional fat than yellow. It also disregards functional and weight differences between the two types. The formula is not adjusted for functional fat or the minimum of required fat. What else? It's very sensitive to mistakes of technique, extremely sensitive, actually, as the results are taken in millimeters. And you've experienced that if you pinch the skin fold or the point in the wrong place, in the wrong way, the wrong angle, if you pull on muscle, that's going to change the skin fold that you have. What else? We know that the accuracy of the skin fold measurement is way more accurate for lean people than obese people. I think that makes sense because when you have a skin fold, the bigger the skin fold is, the more place for mistakes that you have. You might be missing, you might actually not even feel the muscle. What else? Then you need two different formulas to get to the outcome that you want. Every formula includes a mistake in it, so that increases your mistake. So there's a lot of mistakes that can be made, and yet we want it to be within 5% mistake of the truth. So in a way, the skin fold test is a prediction based on a prediction. Because of the usage of formulas that are fed with values that are based on a skin fold that is based on an assumption and based on your ability to technically get it right. Then we have BIA, bioelectrical impedance. When you're playing with electricity, it can be complicated. It's quick and easy method to predict body fat. It's a bit problematic. It has a very wide or very, very big range of error. And you are trading convenience, let's say, for accuracy. The idea is to run light electrical current through your body. Obviously, electricity chooses where it goes through, and it's not necessarily the way you want it to work. So it's definitely influenced by the composition of the body, and there's a few assumptions. And we know that fat-free mass contains mostly water, while fat contains very little water. So fat-free mass will have less resistance to an electrical current. By determining the electrical current running through your body, theoretically, we can get an estimation of how much fat-free and fat mass one has. So basically you're saying according to the time that it takes the electrical current to pass through your body, we can estimate how that combination is. And once again, this theory is problematic within itself because the current will follow the path that has least resistance. And that doesn't mean that it's moving through the tissue that you necessarily want it to. So is it really measuring what you want? Once again, every one of these methods has biases, and you have to know them and you have to understand where they're coming from. What else? So you can see that the current chooses its own pathway, and it tends to go to internal tissues rather than subcutaneous or external or peripheral tissues. Then any state of dehydration versus hydration plays a role in the accuracy of BIA. So if someone is dehydrated, you're gonna get less accurate reading. Then you have the ability, the difference between machines using different frequencies. Some want to target the ICF, some want to target the ECF. Some BIA machines will just miss a whole area of the body, so you're not really having the current go through your whole body. If you're holding it in two positions, it might just go from one arm to the other. So you're looking at a whole body estimation according to part of the body. That's problematic. Then we have the emerging machines that try and send the electrical current through the whole body. But there's still the rest of the problems that are associated with BIA. Okay, I'm gonna stop here, and I'll record another part and we'll take it from slide 54.